Once, the universe was viewed as serene and unchanging. But today we know of great cosmic forces, power beyond description. Astronomers believe this power comes from the dark force of giant black holes. Galaxy NGC 1275, a galaxy that could solve the mystery of the most powerful objects in the universe. Jesse Greenstein, co-discoverer of quasars. Tony Reedhead, searching for the source of their power. And John Conway, chosen to lead an international effort using a telescope half the size of the Earth.
And you can't produce an image of NGC 1275 just with one telescope. We have to use telescopes in different continents. So we've got telescopes in Bonn for this experiment, in Germany. We've got Richard Porcus, who's collaborating with us, and he's working there. And then Tiziana Venturi, she's a telescope in Sicily.
Next, on the Astronomers, searching for black holes in the heart of a galaxy.
Tim, do those helium spectra look okay?
As the day ends, another journey of discovery
Dave,
begins.
we want to look at some active galactic nuclei and quasars tonight, and we're going to start off with observations of NGC 1275. Can you put the coordinates in, and I'll go...
Tony Reedhead investigates the most powerful galaxies in the universe. Reedhead will use the 200-inch telescope on Palomar Mountain, one of the world's largest. Tonight, he will probe deep into space, exploring the hearts of galaxies.
Science is certainly an adventure. It's a continual voyage of discovery. It seems to me remarkable that we can do experiments here on Earth and then translate this experience to what's going on a distant star or a distant planet or in a distant galaxy.
The adventure of astronomy unfolds in majestic mystery. Once we thought a galaxy was merely an oasis of billions of stars, floating in quiet serenity. But not all galaxies are so flawlessly elegant. Some have distorted shapes, others ghostly tentacles. Strangest of all are the distant objects that appear as only faint points of light. Quasars look like stars, but are really the centers of the most distant and powerful galaxies. A quasar can outshine 1,000 normal galaxies. To seek the source of this enormous power, astronomers use a different way of seeing. The glare of the visible world conceals the radio universe. A universe detected by radio telescopes, like these at the Very Large Array in New Mexico. The VLA is the most complex radio telescope in the world. Each of these 27 dishes is connected by computer to form a single telescope 20 miles across. The VLA provides a view of the cosmos 5 times more detailed than the optical telescope at Palomar, and it provides a different kind of picture. When the dishes are aimed at a galaxy, detected radio waves form a map revealing unseen regions shining with radio energy. The location and intensity of the radio waves are coded with colors. Through radio telescopes, astronomers have discovered that some galaxies radiate far more energy as radio waves than as light. One such galaxy astronomers call NGC 1275. 1275 is not a quasar, but it bears a family resemblance. Like a quasar, the galaxy produces most of its energy in a tiny region at its core.
An arc minute is 10 kiloparsecs. Yeah. So that's sort of 60 arc minutes.
Tony Reedhead of Caltech is a leader in the study of quasars.
Sometimes think of the whole scale here. But of course we want to go in a lot deeper to the core of NGC 1275 here.
Reedhead views 1275 as a mini quasar.
It would take 10 million years to produce that total energy.
He believes the galaxy's energy arises from the same process that powers quasars.
Well, here you're looking at a region in NGC 1275. And the interesting thing is that it has this very bright and compact active region, which is very bright in the radio. Now, if you looked at this object optically, it doesn't seem all that extraordinary. It's a slightly unusual galaxy, but not very unusual. But it turns out that a very small fraction of galaxies, which look quite ordinary in the optical, when you look at them in the radio, have extraordinarily high radio emission. They're very energetic objects. So the energy that's pouring out of here in the radio is more than the sum total of all the energy that's coming out from the whole galaxy, all the stars in the optical.
Only one thing seems capable of generating so much energy in so small a space: a giant black hole. Enormous black holes may lurk in the hearts of galaxies. Galaxies were born from great clouds of hydrogen gas, brought together by the hand of gravity. At the very center of the cloud, the gas is squeezed ever more dense. If dense enough, a black hole will form. Feeding on the surrounding gas and stars, the black hole can grow to the size of our solar system, and nothing can escape from it, not even light. The gravity of a supermassive black hole could be the engine that powers quasars. But how does the engine work? How can gravity be the source of such enormous energy? The force of gravity wasn't always so mysterious. Visible light was once the only way to see. But then astronomers found a new window, the universe of radio. Jesse Greenstein was a pioneer in the discovery of quasars. He was an astronomer before black holes were even equations on a chalkboard. It was a different universe, a different time.
I'd been interested in astronomy, and I wanted to go on in science. And I got a master's degree at Harvard in 1930, and then all hell had broken loose. I saw people jump out of windows. This was the great bottom, the Depression. Father and grandfather and uncles and so forth beat on me that I ought to be in the family business, that fresh blood would bring back the family fortune. So I tried it for 4 years, and it was a lot of fun. in the sense that I hated it. By 1934, I asked my present wife to marry me, and she said yes, but not if I stayed in business. So I gave that up and became a mere fact finder, and I've enjoyed it ever since.
The search for facts led Greenstein to Pasadena, California. Caltech's Palomar telescope had just been built. Optical astronomers were having a heyday, but radio astronomers had barely begun. With only primitive telescopes, they could not identify the sources of the unusual radio waves they were detecting. Their radio pictures lacked detail. Help came in the early 50s from two optical astronomers working at Palomar, Walter Baade and Rudolf Minkowski.
They fastened on these two great observers at Mount Wilson and Palomar, Walter Baade and Rudolf Minkowski. Great men, completely open to suggestions, with very little theoretical interest, but amazed at the beauties of what they could see in the universe and really turned on by the excitement of things radio astronomers saw that were not obvious.
Using the new Palomar telescope, Baade and Minkowski searched for clues. They discovered that the unusual radio waves often came from peculiar-looking galaxies. One such galaxy was NGC 1275. In their pioneering work, Baade and Minkowski paved the way for younger astronomers like Greenstein.
Baade kept chow dogs of unbelievable ferocity, which would devour strangers. Anybody who laughed loud was liable to lose an arm. Minkowski could not ever stop talking in a conversation, and he filled pauses by a rumble, sort of, and so. Minkowski was not dreadfully well organized. On the other hand, he had a kind of genius, so that if you asked him, what about that letter? He'd say, and he would look at this 2-foot-high pile of scattered papers, and he would lift up the pile and pull out about an inch of papers, open it, and there was the letter. Or there was a plate, and he would reach for the bloody plate, and he would get a magnifier and hold it up against the light box and say, see, and I'd say, where? And he'd say, see, and he had a thumb about 1.5 inches across. He put his thumb on it. I'd say, Christ, don't touch it. Don't touch it. It's all right, Jesse, all right.
Optical astronomers and radio astronomers continued to work hand in hand. Powerful radio sources were pegged to galaxies visible through optical telescopes. For Greenstein and his colleagues, the identification of these intense radio sources became almost routine. Then in 1964, the world of astronomy was rocked by a single discovery. Martin Schmidt and Greenstein had been investigating mysterious radio stars they called quasars. One night, Schmidt discovered what he at first thought was impossible. These quasars weren't stars at all, but the most powerful objects ever seen, shining more brightly than most galaxies.
In the paper that Martin Schmidt and I wrote in 1964, we have in several places the remark, this is much more energy than we can account for. And we don't know where it's from. We imagine, in fact, that there is at the heart of this quasar an object we call X, which is doing it. Object X. And that's the end of it, because we have no explanation.
Today, astronomers believe Object X to be a supermassive black hole. Quasars and black holes are hot topics at astronomical meetings. This one brought astronomers from around the world, including Tony Reedhead from California. Also Arno Witzel from Germany.
It was timescales of weeks or so, where he found his 1 or 2% variability in compact, mainly in compact sources.
Papers were
Receiver,
presented,
also 6
views
centimeter
exchanged.
receiver. And I'll show you briefly here what
The
happened
meeting was judged
during
a
the
success.
last time.
But as with most meetings, the real progress came later. At a nearby restaurant, Reedhead gathers a group of radio astronomers who all have a deep interest in quasar-like galaxies such as NGC 1275.
1275 is an elliptical galaxy, which is about 70,000 light years across. When we look in the center of this object with, for example, the Very Large Array, the VLA, we see that there is a very interesting structure which I'll have to expand here for you. And if I draw out that structure, what we find is that there's a very, very bright core. Now, of course, what we're really interested in is what is the beast in the center that can do this, because it's an enormous luminosity that we're talking about here. It's about 100 billion times the luminosity of the sun. So it's an very high luminosity, and it's coming from a tiny region. Now, the idea is that these are actually fueled by supermassive spinning black holes.
They decide to launch a major investigation of the galaxy.
Which is quite a long way in front, in fact.
The group includes Tiziana Venturi, an astronomer from Italy, and Richard Porcus, working in Germany. John Conway, a postdoctoral fellow at Caltech, has convinced Reedhead that he is ready to lead a major investigation. Now he'll get his chance. The observing team will link radio telescopes in different countries, creating the effect of a single dish thousands of miles across.
So if you want to think of it graphically, you start out with Onslow, okay, and then you go a bit further south, and then there's the 100-meter telescope in Bonn, okay, and then a bit further south than that, there's the 32-meter telescope in Noto in Sicily, okay, and then those are the 3 telescopes that we had in Europe. And then you come across the country, and there's a telescope in Haystack, which is Massachusetts, and the VLA, and 2 new telescopes of the VLBA near the VLA at Pie Town and at Kitt Peak, and then the Owens Valley Radio Telescope. The Owens Valley Radio Telescope. The Owens Valley Radio Telescope, right? This was the center of the nerve center.
If the team is successful, they will create an instrument thousands of times more powerful than the 200-inch Palomar telescope. The linkage of radio telescopes is called Very Long Baseline Interferometry, or VLBI. As the Earth turns, the telescopes in Europe will be the first to detect the galaxy. The network of telescopes will span 6,000 miles, forming a system that sees as clearly as a dish almost as large as the Earth.
Here in beautiful Bishop, California. It's about 25 now past 6 on a beautiful High Sierra day, and again, big fine 6.
In the observations, they can get in touch with me. I'm the central person to coordinate things. And that's basically what the PI does. And usually the PI also does most of the analysis afterwards.
Conway has come to the observatory located in Owens Valley, California. It is one day before the observation of NGC 1275 is due to begin.
But NGC 1275, it's one of the closest objects and therefore one of the brightest. Also, we've got the highest sort of linear resolution. You can see the most sort of detail in terms of what we can resolve in terms of light years. And so it's very obvious source to study. But because it's very close and we get high resolution, it's also very complicated. which means it's hard to get very reliable images of it. We'd like to get really reliable images because these tell us all sorts of things about the motions which are going on inside.
For a young astronomer like me, it's very difficult because there are only a few permanent jobs in the subject. I mean, you work for 2 or 3 years in one place, and then generally you have to move somewhere else. For a long time, I wanted to be an astronomer, and you start thinking about going out and getting a real job sometimes. But then I don't know really. It's got something, just looking at the universe.
Conway has a lot riding on this experiment, but he's not going to play it safe. He's going to try something different. In his PhD work in England, Conway proposed a new method to make VLBI even more powerful. This experiment will give him the chance to prove his idea works. The technique requires changing the detectors at each site so that they can observe at more frequencies than normal. The extra work doesn't bother Conway. It's the weather he fears. If it rains on any of the telescopes, the data could be washed out.
The problem is that particular frequency affects use of water vapor in the atmosphere, which can reduce the sensitivity and causes problems. If the weather's bad at a lot of the sites, then it really affects the experiment.
To Conway, this observation has become more than a test of his concept. It's become a test of himself, a rite of passage.
The whole point about it is this accumulation of knowledge, that everybody makes their own observations, and eventually it becomes part of the total knowledge. When you look back over a long enough timescale, you say, well, where have we come in the last 10 years? And you find that we've actually discovered quite a lot about these objects, and we've actually made a lot of new discoveries. We know that everything's going to get better, We know that when we do this experiment a year from now, we're going to have more telescopes, we're going to refine our techniques, we know that the data is going to be better, we know we're going to get better images. So I'm optimistic that we're supposed to be in 10 years' time, we will have made just as much progress as made in the last 10 years.
The coast of Sicily. Tiziana Venturi is traveling to the radio telescope near the town of Noto.
You always have the opportunity of getting to travel a lot. This is something which is really, I really like, I'm really enthusiastic about that.
Venturi is an Italian from Bologna, now working at Caltech. On her first trip to Sicily, she passes through the ancient city of Siracusa. For most VLBI observations, technicians can operate the telescopes unaided. But Conway wants nothing to go wrong. Venturi has agreed to supervise directly.
We are waiting for the run to start. So at that point, our observation will start, and then it will carry on like for, I think, 18 hours or something like that. So this is now it's just very, very tedious stuff. You don't really have to do anything except writing down like the system temperature, the antenna temperature, and you have to stay up hours and hours and changing the tape every 4 hours and keep on checking. It's really boring. In radio astronomy, you have to wait for months. In VLBI, it's even worse because then, since all these radio telescopes are independent, then you have to correlate your signal, and this requires time, and then you have to reduce stuff. And it sometimes takes you like 6 or 7 months before you get an image and before you realize whether all your efforts were worth.
Bonn, Germany, the birthplace of Beethoven. Overseeing the German link in the experiment to observe galaxy 1275 is Arno Witzel of the Max Planck Institute.
If you look at the optical picture of NGC 1275, it is sort of chaotic, but it is beautiful, there's no doubt. That's another meaning which it has to me. And then it is kind of a challenge. We still don't know what the physical processes finally are, which make such energies. We have ideas about it, and I'm sure you will hear a lot about that, but we don't finally know it yet. And so it is a challenge, and I think it will be for some years. Mankind lives for 100 years, if we are very optimistic. But cosmical processes normally take place in millions and billions of years. If we look to several points, to very many points actually, we see galaxies at all stages of their life. When they are being born, when they evolve, finally when they die. It takes me only something like half an hour drive to go from the institute, the Max Planck Institute, which runs the telescope, to the site here in Effelsberg. So we have both. We have the telescope nearby, close by, and we have a beautiful surrounding whenever we go out there. So over there we have our nice little toy, the world's biggest steerable radio telescope. It was built in the late 60s, actually between 69 and 71, at incredibly low cost, one should say nowadays. It was about 30 million Deutschmarks at the time being, which is nothing for such a beast, I think. And it has an enormous collecting area. The area over there of the surface is bigger than the area of a soccer or a football field for the Americans. We are setting up an experiment on the Seyfert galaxy NGC 1275, and the astronomer who leads that experiment here in Bonn is Dr. Richard Porkes, whom you see over there in his green shirt.
We know clearly that in the case of quasars, just to get the energy out, there must be a very, very compact and massive object at the center. It may be a black hole, it may not be a black hole, we don't know, but it must be very massive. And also in the case of NGC 1275, that's clearly the case also. We see signs of the same sort of activity as in quasars, especially in the radio. And exactly what the relationship between these different classes of galaxies is, I can't tell you.
The instruments have been fine-tuned, the telescopes aimed, the computers are all in readiness. Now, before the investigation can begin, the astronomers must wait. Wait for a galaxy 200 million light years away to rise into view.
2.65. 10. Yep. Radiometer. Both meters are in scale, yeah.
Poi questa è la schedula che ha mandato John Conway.
The galaxy 1275 has been detected in Europe. There, telescopes have picked it up and are tracking.
In Europe, it's now well overhead, but here it's just groveling around the horizon. Yeah. So it's very close now. Yes, and in fact, yes, okay, great, we're tracking now, so you actually pick up the source. It's just come over the horizon, and great, the program started.
VLBI observations are not like looking through an optical telescope. All the telescope signals must be combined later. Only then will they know if the experiment has worked. They must observe blindly. So some take life easy, while others keep checking and double-checking.
40, 50, 60, 70, 80. 0, 10, 20, 30. Looking at things like NGC 1275, you've got to have some sort of picture of what's actually happening, otherwise you can't make sense of anything. So it's a key to actually imagine being there. And if you can imagine being there, then you can hopefully get more science out.
No human could survive a journey into the core of a galaxy. But we can imagine what it would be like. Near the core, stars crowd together, and the gas between them grows denser. The temperature rises to heat a surrounding cloud of gas. Beyond this veil lies the supermassive black hole. Around the black hole spins a vortex of gas and stars, swirling towards oblivion. No radiation can escape from the black hole. Astronomers would see only the spinning disk around it. Stars and gas orbiting close to the center risk being drawn into the black hole. Stars trapped nearby are doomed. Some of the material is shot outward in a great jet of high-energy particles. To astronomers, these jets are beacons pointing to the black hole heart of the galaxy. Three o'clock in the morning, 6 hours into the observation. Conway discovers that a piece of equipment has been malfunctioning. Now he wonders if he's been observing anything at all.
Disconnected the 5-meter telescope from the network.
Yeah, they thought that was what was causing the crash.
I still think it. Special ports like the one used to control the 40-meter have to be configured in a special way.
I think 3C73 is still up. I'll try it. Oh, okay. Seems to work. Basically, there's just a piece of equipment hadn't been connected properly. So that means most of the calibration information up to now has not good. But I don't think it's actually affected the data we've got, so that's the main thing. It's like, it's bad, but it's not a disaster. We've got the data, I think. So that's the main thing. And hopefully it should be a boring night from now on.
We just don't know yet, of course. There's always this problem when you observe that, especially with VLBI, you're never quite sure that you're doing it right. You're sitting here, sometimes doing nothing and just hoping that the thing is working.
The antenna is working perfectly, and all the numbers are, I mean, sort of what we expect. That's pretty good, yeah.
I dabbled in amateur astronomy and stuff. I remember at school I was a member of the Astronomy Society and stuff. But the problem was that I like the idea of amateur astronomy, but it was just too cold, you know. And but then I got interested again when I got interested in the physics of what was going on. So I come back to it, and it's not quite as cold when you're doing it professionally.
Well, I don't really feel fortunate because I'm an astronomer. I just feel fortunate because I'm doing what I wanted to do. Astronomy and physics and all these other scientific disciplines and subjects are important in the same way like paintings and philosophy and literature. What I feel is that, I mean, even if in sort of small amounts, but I'm contributing to this, or also all the astronomers really are contributing to this overall knowledge. And this is what astronomers do and what other people in any other discipline do.
There are always people who want to do an experiment which shows a theory wrong, and I think I would cast myself more in that line than those who are trying to confirm a theory. But it's merely a question of outlook. I mean, it doesn't affect what the result of the experiment is, of course. Maybe it affects what experiments you choose to do.
Ah, ho capito. E che numero dovrebbe... Cioè, io non le so proprio queste cose. Un orrore. Io, cioè, appena vedevo un numerino, una notte ho svegliato.
This experiment may test a favored theory that black holes are fueled by other galaxies.
One of the reasons why it is thought that, I mean, galaxies in the center of clusters of galaxies are bigger and more massive simply because they accrete material by interaction with other galaxies, and therefore, I mean, they just collect more material, more gas and everything, and that they just get bigger and bigger. And that's the case for NGC 1275 too, since it's at the center of this rich cluster of galaxies.
Galaxies are rarely born alone. Usually they come in clusters. Sometimes they interact. A larger galaxy may cannibalize a smaller one, gaining new material to feed its black hole. The black hole attracts the gas and stars of the smaller galaxy. The infalling material joins the rotating disk, heating it still further. The material that feeds the jets is ejected at nearly the speed of light. The black hole and its disk have become the most powerful cosmic engine in the universe.
Sarò lì.
Saranno pane quotidiano.
Dio, che orrore, non farmici pensare, guarda. Una piccola schifezzina. Però noi le uniche informazioni.
So far, the observation has gone well. But now, with 4 more hours to go, a slow-moving storm is spreading rain over northern Europe, affecting the telescopes in Germany and Sweden.
This is when we did a check to make sure we were on NGC 1275. We do a cross-scan procedure whereby we just drive across the source and we hope that the source peaks up in the middle. Well, it more or less does here. This is the characteristic response you get when you drive across the source. And further back, you'll see here that the output level went off scale because there was rain.
Okay, I just thought I'd mention that, just to be sure. Okay. Okay, well, if you can't... Okay, thanks anyway. Bye. Okay, the weather wasn't very good then. And didn't have time to make some of the calibration measurements they would like, but that's okay. That was Sweden, yeah. Yeah.
This experiment is a rare opportunity. It offers the best chance to explore the power source of 1275. Astronomers believe it may also help explain the far more distant and powerful quasars.
Quasars are very interesting objects since, on the one hand, they are the most distant objects in the universe we know, which also means that they were produced very long time ago. And the very fact that we see them here on Earth means that they have to be enormously powerful. And in fact, they are the most powerful objects in the whole universe we know of. This is VLBI observations of quasars. Look at these marvelous jets here. You see we have regions here shown in different colors of different temperature, of different energy. This proves that we have a source of very intense radiation. And from theoretical considerations, you can show that it has to be gravitational energy, something like a black hole, a supermassive object, since the efficiency of nuclear processes is not sufficient to produce that sort of energy.
Astronomers seeking to understand quasars found an easier target in 1275. The galaxy is relatively nearby and has a quasar-like heart. The first VLBI maps of 1275 revealed an immense radio-emitting region surrounding the core. It was the core that most intrigued astronomers. The investigations probed more deeply, showing greater and greater detail. Increased magnification revealed a complex and chaotic structure. Then Reedhead and Venturi, together with colleagues from Berkeley, made a sequence of maps. It became clear that there was a stable, unchanging region to the north. This is where Conway is aiming his search. If a black hole exists, it will be found here.
So it's nearly over now. Posso togliere il nastrino? Grazie.
Time is up. With the observation over, the team can finally rest. At each site, the data has been recorded on ordinary videotapes. These tapes will be sent to Conway to begin the key phase in the process.
Okay, that's good. I was just a bit worried about that. So.
Okay.
Great, it's finished.
Stop the tape.
Okay, stop the tape. Stop. Okay.
Okay, good.
Conway will analyze the tapes at Caltech to discover whether he has the data to continue. The analysis will take weeks, but it could create a new map from which a new theory could emerge.
There's not much point in just observing things if you don't try to interpret them. And in fact, the main joy of the whole enterprise comes in the interpretation. It's a lot of work to make these observations. When you've finally got a map and you can sit down and try to interpret it, that's the payoff. Science actually involves not only just a lot of cerebral thinking, but there's a lot of practical aspects of science as well. And you really have to keep your feet firmly on the ground if you're going to make any worthwhile contribution to science.
Reedhead is like many scientists who have made their mark. He finds much of his time is taken up by paperwork. He must search for funds, write proposals, and serve on committees.
The administration is something that none of us really wants to do, but it's a price that we have to pay for being able to do science. And obviously when I was a graduate student and when I was a postdoc, there were other people who were paying this price so that I could spend most of my time doing research. And of course, as one gets into a role where you have to do some of the administration oneself, we try to keep it to a minimum, but we can't avoid it entirely. And but there is also a positive side of it, which is that you tend to end up interacting with more people. But given a free choice, I would much prefer to spend 100% of my time actually doing research as I was when I was a postdoc. When John first came into the group, I made a number of suggestions of things that I thought he might work on, and certainly that I would have liked him to work on, and some of them he was quite interested in, and some he wasn't. I realized that there was this work that he'd done, obviously, for his PhD, which could be applied to this object, NGC 1275, that Tiziano and I had been mapping. And of course, I suggested that to him, and he took off. I mean, there was no holding him back. I'm sure that I was very much the same as what John is now. When I came to Caltech as a postdoc in 1974, I was looking then for exciting new possibilities in very long baseline interferometry, and I was very fortunate that there were such possibilities. We made some exciting observations then. There is a little tug. Here's this project, you've done all this work. Now, do you want to hand the project over? Now, of course, you have to do that sort of thing, because in this case, there's a brand new technique which could best be exploited on this object. But the only person who's around, who's going to put the effort in and make that technique work is obviously John.
Conway's next task takes him to a Caltech basement. Here, the tapes from all the telescopes will be played together. It's called correlating. If they match, he will know his idea worked and that he has the data to go on.
And basically what we're trying to do here is we're trying to compare the random noise we get at the two different telescopes. And depending on how correlated it is, we know the sort of structure is like. So what we do here is we take these tapes and we try and play them back at the same time from the different stations, so like Bonn, Owens Valley and Noto. And we try and compare the signals on the tapes.
Conway will be looking for fringes, the telltale signs that the telescopes were synchronized and working together. No fringes means no data. Venturi has been here before. She knows how it feels, waiting for a computer to tell you whether you've succeeded or failed.
I mean, we thought we'd lost some of the tapes from this experiment. We've got so many for this experiment, such a long experiment. And we eventually found them in a drawer downstairs, which they hadn't been sort of logged in properly. So, and lots of things happen like that that tell us the tapes get sent to the wrong place, or they get mislaid, or, I mean, all sorts of minor problems, you know.
Well, that's 3 out of 3 so far.
They're short baselines.
The first series of tapes shows nothing. Not unusual, but not encouraging either.
Yeah, okay, well, we'll see. But we'll send it mechanically or... Human error.
Yeah, human error.
Okay, John, here's 4 of the tapes we're going to need. This Owens Valley. And VLA. I think I got the right tapes playing this time.
Why you had the wrong tapes?
I forgot the orders commuted from the haystack and gone.
Yes,
There we go.
wow, that's a fringe.
Huge.
Oh, that's more like it.
That's
Yeah,
more like
that's
it.
what we like to see.
Yeah.
This raw data allows a multitude of maps to be made. Conway's biggest challenge is to decide which will be most useful.
That's why it was also what I suggested, John. Because how many
His judgment is debated by his colleagues.
4 years from, yeah.
From 85, anyway.
You may expect things to always appear at roughly the same point.
Yeah.
Even at this early stage, Reedhead can tell that Conway's map shows great promise.
I mean, the most recent map has this kind of exactly the same position.
Ah, well, this is a little bit bigger. Good point.
Because there were a little...
This is only a few days old, and typically it takes weeks, months sometimes to process a data set so that you're really happy with it and you know you got everything out of it. And in fact, we've only got part of the data in this actual map.
We've now found this very stable configuration right near the central engine, and then we're seeing further out than that the material flowing out at half the speed of light. And I think it's the first time that we've got close enough, as John has said, in an active nucleus to be able to see something that may be tied to the real engine in there and maybe telling us something about it.
All this stuff here is not real. All these stringy things, these are data errors which have to be taken out. Most of the structure in here is real, and we talked about that. This is where the black hole is, we think, and these features have been very stable over time. Now, this feature and this feature might be real because they're much brighter than anything else in the rest of the image, but we don't know yet. And one of the things we've got to do is we've got to carry on processing data, add more data collected, and see if these features stay there or if they go away.
Conway's map adds to speculation that 1275 could in fact be 2 galaxies. Perhaps there are even 2 black holes. This would fit a recent theory that multiple black holes may cause once peaceful galaxies to erupt into blazing quasars. The heart of NGC 1275 could be twin black holes locked in orbit. Speculation now, but guided by Conway's map, it's a possibility that future observations should clarify.
So badly collimated, really.
For the present, though, the observation succeeded. Conway's idea worked. The map he made is the best yet. This is what all astronomers hope for, to take one more step along the journey of discovery.
Presumably, therefore, dims it. You're assuming a fairly large brightening due to the approach, and nothing is happening on the other side.
Well, yeah, I mean, yes, I mean, one hypothesis is there are 2 jets, and we only see one.
All of astronomy has always worked that way, as the work of single individuals with imagination trying new things. And often they do get late in life burdened with teams of 100 people maybe, but at heart they're single go-getters. So I hope you can understand how we live from moment to moment with all these miserable, dirty little facts, none of which we properly understand until suddenly a vision of regularity appears. And at every moment in science, you go through this and you think you're there. Now the black hole is the click, and I'm not sure it's the end. The mind of man is the soul or spirit or whatever is infinite in his grasp. The universe may be only finite. At least there is no limit to what we've been able to imagine so far.